Hi, my name is Chris Nigh, and on behalf of my co-authors, Bhargava and Blanton, I am presenting our work AAA, Automated on-ATE AI Debug of Scan Chain Failures. When a new integrated circuit product is introduced, there are many tests that must first be evaluated. Each of these tests will undergo some initial data collection, which often includes SHMU collection, margin analysis, and if necessary, fail log collection. If the test is deemed stable, it could be enabled in a production high-volume test program. However, if the test is not, it must undergo root cause debug to identify the issue and then regeneration to address the issue. The regenerated tests will go through the same evaluation process. This procedural loop of evaluation, debug, and regeneration may repeat many times if there is insufficient data to accurately root cause the issue or if there are multiple potential issues with the test. The task of debug is a cross-domain activity, often involving information from many sources. The ability to execute tests and collect data using automated test equipment, or ATE, is essential, as is information from design for test, or DFT. It is also very common for EDA tools for diagnosis or detailed design analysis, like layout or timing, to play a significant role in debug. One approach for debug is to compose a team with specialist representatives from each of the required domains. Through much brainstorming and discussion, these engineers are likely to come to a hypothesis that can be investigated through additional experimentation. Conversely, there also exist debug experts that have been involved in many prior debug instances. These experts will be able to more quickly and easily connect meaningful dots as they draw upon their great knowledge to construct hypotheses, which tend to be more accurate and incisive than that of a non-expert debugger. When debug is performed, there are typically 4 pieces of information that are most helpful in approaching a potential root cause. First, the failure class provides a high-level description for the failure. Second, we are interested in the failure location. This will be part of the circuit where the failure originates or is observed. Third, we would like to know how the failure behavior changes over test conditions. This objective describes the way in which environment parameters like voltage or frequency impact the way the failure behaves. Lastly, the failure behavior over test stimulus will also be helpful for debug. This objective typically targets a fault model description of the failure. Modern IC products have an enormous volume of tests, where many different cores must undergo multiple tests across multiple performance modes. Even for a test population where the vast majority are stable upon initial evaluation, a small percentage of such a high volume of tests still leads to significant debug effort requirements. Furthermore, the rate at which this test volume increases is only expected to accelerate in the coming decade. The 2019 Heterogeneous Integration Roadmap predicts a 10x increase in test time between now and 2031. As it stands currently, there are often not enough debug efforts to support all required debug activities across the many products of a company. So how can we expect our current debug methodologies to keep up with those monstrous and only increasing test volumes? Thus, our objective, to automate the procedure that a debug expert would follow during initial collection of failure debug objectives. Our proposed solution is to integrate the many required sources, specifically ATE's ability to execute tests and collect data, DFT's ability to interpret the results of that data, and EDA tools' ability to incorporate low-level design information, all into a full expert system for failing test debug. With this, we propose AAA, Automated on-ATE AI for failing test debug. To operate this system, the user will first provide an objective to the tool. AAA's inference engine receives the objective. It will then work with the expert-defined rules in its knowledge base and the pieces of information in its database of facts to identify the results of this objective. As a main source of facts, AAA is integrated with multiple external tools. When a rule is encountered which requires test results from the ATE, AAA will send commands to an online ATE with a device under test and receive the test results. When a rule requires information about the design for test structures, a database of commonly used information like scan chain configuration and scan cell instances is queried. When needed, AAA can also interface with a commercial diagnosis tool to provide ATE failing cycles for diagnosis and receive the resulting diagnosis suspects. When a final result is achieved by AAA, it is returned back to the original user. We believe that AAA can provide multiple potential benefits. First and foremost, The automated and on-ATE nature of this system provides the opportunity to vastly accelerate initial data collection. This will in turn reduce time to resolution of the failing test debug. This can also help ensure that debug experts are not spending time on common standard debugs, but are instead focusing their efforts on more complex and interesting debug tasks. Next, in an organization with many concurrent projects, it may be common for there to be many separate debug efforts going on concurrently. Sometimes, there are valuable debug methodologies that are commonly used and deployed by one team that may not be effectively communicated or set up for other products. AAA can act as a centralized repository for debug techniques and expertise to enable propagation of benefits across all teams and products. As more novel debug cases are experienced, AAA will become more comprehensive and ultimately more valuable to the organization. Finally, the nature of expert systems provides for a high degree of explainability. This enables non-expert users to study the behavior of AAA to better understand how debug experts think about debug problems. This provides a pathway for non-experts to become debug experts themselves without having to go through their own debug challenges and without training from debug experts. In this work, we use AAA to target failures related to the scan chain. Scan-based tests provide the most significant structural coverage of the design, therefore making correct scan chain operation an essential first step in new product bring-up. The design for test architecture of the study designs supports a compressed mode used for the vast majority of coverage-based scan testing. There also exists an uncompressed mode, which bypasses the decompressor and compressor to provide improved controllability and observability. To extract the first debug objective, the user will simply ask AAA for the failure class, and AAA will use a set of 3 tests to decide from a set of 5 possible failure classes. As an example, when both chain tests fail, it must be determined whether the failure is a degenerate catastrophic failure more likely related to setup of ATE or the test itself, or a more typical scan chain failure. To make this classification, debug experts will perform a manual check of the fail log in the compressed mode chain test to determine if approximately half of the early test cycles are failing. To replicate this, AAA counts the number of early fail cycles per pin and returns a catastrophic failure class if more than 40% of those cycles are found to fail, and a scan chain failure class otherwise. Next, the user can ask AAA for the location of the failure. To achieve this, AAA has a suite of 3 different techniques that can be deployed. First, the per-chain masking capabilities of the compressor can be used to deterministically identify the failing compressed mode scan chain. While this technique is confidently reliable, its inability to go beyond the scan chain leaves precision on the table. Next, the technique of test condition modulation can be used. In this method, the scan chains are loaded at a voltage and frequency condition where the chain test is passing. Then, the test condition is changed to set to the failing target condition, and a clock pulse is sent to excite and capture the failure effect in a single scan cell. Finally, the chains are unloaded at the passing test condition to identify the bit position of the failure observation. While this provides highly precise results, this method is only applicable where there is a passing test condition to use for the shift procedure. Lastly, AAA can link to commercial diagnosis tools to execute a diagnosis run using the results from logic tests. The precision and accuracy of those results may vary depending on the distinguishing capabilities of the logic tests, but it will often be able to narrow down the set of potential failing scan cells from the full chain. However, there is runtime and compute overhead with the execution of EDA tools, so this is deployed only if necessary. For the next objective, the user will ask AAA how voltage and frequency impact the pass-fail behavior of the test. To extract this, AAA will perform minimum passing voltage and maximum passing frequency identification. With the results, the negative margins to the target voltage frequency condition are identified and returned to the user. Next, the existence of these margins is used to provide a high-level picture for the shape of the shmoo. For example, if there is no frequency for which the test passes at the target voltage, the failure is said to be frequency independent. This behavior is translated to a description of a shmoo commonly used by the debug expert and provided back to the user. For the final objective of failure behavior over test stimulus, the user will ask AAA for a fault model that describes the failure. AAA leverages the uncompressed scan chain mode for controllability and observability and supplies a repeated 0011 stimulus to the scan chains. Through this stimulus, each scan cell will experience a regular and repeated set of the 4 possible bit value transitions. An analysis of the locations of the resulting failing cycles can be used to identify and classify a fault model. For example, a stuck at 0 fault model at any point along the scan chain will result in failing cycles for all expected 1 compares. Similarly, a bidirectional hold fault model will fail for every odd cycle in the resulting compares. The identified fault model is then returned to the user. To validate AAA, we performed debug extraction on a set of devices with scan chain failures. This was executed on one core with 1.6 million gates from an industrial design, and an online tester was used to collect data for analysis. The table compares execution times for various objectives with estimated average execution times from focused manual debug. Once time is spent creating a test, that test can be reused, making subsequent executions of a task faster than the first. We observed significant runtime savings, in some cases reducing task execution time by more than an order of magnitude. It is also worth noting that manual debug may be susceptible to other sources of delays, including equipment availability, time zone logistic challenges, and other higher debug priorities. To summarize, new product bring-up requires debug a failing test, which is greatly aided by debug experts. But the significant and increasing test volume makes it so that debug experts cannot support all ongoing activities. To address this, AAA is an expert system for failure debug that integrates ATE, DFT, and EDA diagnosis. It offers multiple potential benefits to the debug and bring-up process. This work has been validated on scan chain failures from an industrial design, and future work plans to expand the system to address other types of failures. Thank you very much for your time, and we hope you enjoyed this presentation.